Okay, we're going to try this again. I had made a video of the content here and ended up being about 25 minutes long, and I don't think any of you really want to listen to me for that long. But what I'd like to talk to you about today are electron configurations. And this right here, whoops, let's put a pen on. Okay, this right here is what we call an electron configuration. And the questions that I have for you is, what do the letters and the numbers stand for in this configuration here? And secondly, what rules govern how you and I are going to write these out? Okay, those are the, if you listen to this and understand these two questions by the time I'm done, I'm going to be happy. So, what do the letters and numbers mean? Well, if we take an element here, and the element that I have here is potassium. Potassium has an atomic number of 19, which means there are 19 protons, and since potassium is neutral, it has also 19 electrons. Okay? So if I write the configuration for potassium, I would write 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. That's the configuration for potassium. So when we take a look at what these symbols represent, the numbers that are in front of letters. So here, if I'm looking at the numbers in front of the letters, I'm looking at the 1, the 2, the 3, and the 4. These represent the principal energy level that you find the electron in. Okay, the letters, and the letters here, let's do this in green. The letters are an S, a P, S, P, S, S, and if I did right, I'd find that there's more letters than that. You have S, P, and then D and F. And these are types of orbitals. Okay? Another word that you're probably going to hear thrown around, these are sublevels, that the energy level is divided into sublevels that have different types of orbitals. And then the superscript letters, which we will do in yellow, these numbers right here, you've got 2, 2, 6, 2, 6, 1. The superscript letters represent the numbers, or the numbers of electrons. Okay? So that's what the letters stand for here, the numbers, at least the numbers of electrons in that particular sublevel, or in those types of orbitals in that energy level. Okay? So, how do I write this out? We have rules. The rule that you probably need to understand first is the Aufbau principle. And the Aufbau principle says that the electrons are going to fill orbitals of lowest energy first, and that's what you see from this diagram. I've got energy on the side here, and the first energy level or sublevel that fills is a 1s, and then 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. But tell me this, what do you see happening here? If you're looking at it, you see what I see. The 4s has got a lower energy level than the 3d, so that when we're writing these configurations out, if we follow the Aufbau principle, then the 4s fills before you get to 3d. Okay, and we'll take a look at that as we go here. But notice that the sublevels within each energy level have different energy values. The S is typically the lowest, then P, then D, then F. But there's overlap between one energy level with another energy level. Two other rules are the Pauli exclusion principle, and that says that the orbitals can only hold 2 electrons, and then they're full. You can't put 3 or 4 in there. Sometimes you can put 1 in, or it can be empty, but at most you can put 2 electrons in it. And Hund's rule says that the electrons are going to fill empty orbitals in the sublevel before they start filling an orbital already holding an electron. And I'll show you an example of that. You might also want to talk to Mr. Meehan because he has this great bus analogy that you're going to love. I have a different analogy, but I really can't say it at this point. Okay? So, this is another way of looking at the diagram that I had up before. And my question to you is that how many orbitals do each type of sublevel hold? When we look at an S sublevel, you have the 1s, 2s, 3s, 4s, 5s, 6s, 7s. How many orbitals are there? And here in this diagram, every dashed line represents an orbital. So in the 1s, how many S-type orbitals are there? And in all sublevels, you only have one S sublevel. For a P, how many dashed lines are in the P sublevels? I see 3. In the D, I see 5. And in the F, I see 7. Now, if each orbital can at most hold 2 electrons, how many electrons can an S sublevel hold? That's right, 2 electrons. A p-type, it can hold 6 electrons before it's filled. D is 10 electrons, and F is 14 electrons. Does that make sense? This diagram is a little bit different in that the S's are all aligned, the P's are all aligned, D's are all aligned, and the F is all aligned. In the previous diagram, you had what was aligned were the energy levels. 1, 2, 3, 4, 5, 6. So, now if I'm going to write out a configuration, I need to follow the order of filling, and this is what we call a diagonal rule. Okay, and it shows the order that electrons fill energy levels and sublevels. For example, if I take oxygen, oxygen has an atomic number equal to 8. That means there's 8 electrons in oxygen's electron shell. So if I'm going to follow the diagonal rule, I'm going to start here with the 1s, and I write 1s, 2 electrons in there, it's filled. I can't put any more in there. So this tells me that I have 2 electrons in an S-type orbital in the first energy level. Next, I'm going to write 2s and then 2, because I still have 8 electrons to show, but now that's filled. Okay, so I've got 2 electrons in a 2s sublevel in the second energy level. What comes next is I go, if I've done that one, next one is, if I'm following the arrows here, it's 2p. And I write 2p, and how many electrons can I put in there? Well, you say I can put 6 in there, but 2 plus 2 plus 6 would be 10. And I don't have 10 electrons, I only have 8. So I write a 4 there. 2 plus 2 plus 4 is 8. If you add these numbers together, when you're done, you should come up with a number equal to the atomic number. The other way I can show this is by an orbital filling diagram. And so here, each line represents an orbital. And I have 1 orbital in the 1s, 1 orbital in the 2s, and I have 3 orbitals in the 2p. Okay? Now, here we use an up arrow and a down arrow to represent the electrons. The up and down represents the spin that each electron has. So here that's filled, this is filled, and when I get to oxygen, according to Hund's rule, I can go 1, 2, 3, and then I'll pair that last one. But these two are not going to be paired together. They will occupy empty orbitals before they will bunk up with another electron. Okay? The question I have here is, what connections do you see between electron configurations and the periodic table? Now, if you've ever wondered why the periodic table is shaped the way it is, let me ask you this question. For an S-type sublevel, how many electrons can it hold? 2, right? Well, guess what? I have 1, 2 columns in the S block. Is that a coincidence? How about this one? This is your P, that's green. I can hold 6 electrons in the P. 1, 2, 3, 4, 5, 6. Holy smokes. Maybe there's a connection between the periodic table and electron configuration. Let's do D. D can hold 10 electrons, right? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yikes. Let's try this one. I can have, in the F, we can hold 14 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Wait a minute. What's going on here? Well, I'm not going to tell you, but if you look at your periodic table, see if you can figure out why these have 15 elements, and is that true for all periodic tables? I mean, look at the ones that you have access to. Okay? So, can we do this? If I gave you the element selenium and told you that its atomic number is 34, could you do this? Could you write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, 10, 20, 30, 4p4. And if I was going to do the electron filling diagram, or the orbital diagram, I'm going to pick my outermost energy level, because these are the electrons that we are primarily interested in chemistry. These are the ones that actually get to play chemistry with other atoms. I'm going to look at this, and I've got 2 electrons there, and in the P, I've got 1, 2, 3, 4. And that would be the 4s and the 4p. So if you have questions, get into class and ask your teacher. Okay, thank you very much.